Today's class, we are going to study about the Ampere's law. Let me tell you, it is analogous to the Gauss's law for electrostatics. Now, according to the Ampere's law, for a closed loop of any shape, irrespective of the shape of the loop, for a closed loop of any shape, the line integral of the magnetic field, that is closed integral B dot dl. Closed integral B dot dl, the line integral of the magnetic field, is equal to mu 0 times the current enclosed by the Ampere loop. For a closed loop of any shape, the line integral B dot dl is equal to mu 0 times the current enclosed by the loop. Okay, let us see an example here. See, this is a current I1 that is directed into the plane of the board. The current is directed into the plane of the board. Now I am considering a current I2 that also is directed into the board. Now I am taking another current I3 that is directed out of the plane of the board. Now I am considering a loop. So this is a closed loop. So this is a very important closed loop of any shape. So let us calculate what is okay. So closed integral, I am considering the shape of the loop likewise. The shape of the loop likewise I am considering. So here closed integral B dot dl. Closed integral B dot dl is equal to mu 0 times the current enclosed. See, this question has some tricky concepts in it. So there are currents with the opposite direction. So we need to choose one current as positive and we need to choose another current as negative. Now, as the magnetic field is directed into the board, as we have seen with the current element, the thumb should represent the direction of current, means the curved fingers represent the direction of magnetic field. So we will take those magnetic field along the direction of the loop, as positive. So magnetic field produced by currents along the direction of the loop. I repeat, magnetic fields produced by current along the loop is positive. So here the field due to I1 is in the same direction, so I1 can be taken as positive. So will be the case with I2, that also will be the same sense, magnetic field, and if you take a point here, the direction of the magnetic field will be likewise using the rule. And so I1 is positive, I2 is positive, now I3 is negative. Now you can see that the currents I1, I2 and I3 are enclosed by the Amperian loop. Does it mean that where these currents are located? No, nothing likewise. It is important only that the currents must be enclosed by our Amperian loop. Currents must be enclosed by our Amperian loop, irrespective of where that current is enclosed. Ready? So for this question, the answer is mu 0 times I1 plus I2 minus I3. Now, I would like to tell you an important point that Ampere's law is an effective tool wherever the system has some kind of symmetry, like I said with Gauss's law. So Ampere's law is an effective tool for determining the current, electric current, wherever the system has some kind of symmetry. So let us use the steps to study Ampere's law. The first and most important requirement to study Ampere loop is identify a suitable Amperian loop. Amperian loop which I am writing as loop itself. Identify a suitable loop. That is one. Then second point is, you have to choose the loop in such a way that the loop is chosen such a way that magnetic field is tangential to the loop, tangential to the loop as far as possible, also I believe possible, tangential to the loop and has a constant magnitude. The magnetic field has a constant magnitude. The loop is chosen in such a way that the field is tangential to the loop and has got a constant magnitude. That is second point regarding Ampere's law. That means what will be closed integral B dot dl is equal to. So B is tangential. So if you consider this one, here B is in this direction, dl is also in the same direction. So closed integral B dot dl in that situation reduces to the form B into L, where L is the length of the loop. L is the length of the loop. Now I can say that is equal to B into B dot dl is B into L. That is equal to mu 0 times I enclosed. Right? That is mu 0 times I enclosed, or I can say magnetic field B. Okay, magnetic field B is equal to. In this situation, I am going to get the magnetic field B is equal to mu 0 I enclosed divided by length of the Amperian loop. So we have to use S and so the steps, let us revise once more. The first step to apply Ampere's law is to identify a suitable loop. I say suitable means it should be a symmetrical loop. The loop must be a symmetrical one. The loop is chosen in such a way that the magnetic field is always tangential to the loop and has a constant magnitude. Now, as a result of constant magnitude and it is along the loop, B dot dl generally reduces as B into L, which is equal to mu 0 I enclosed, or B is equal to mu 0 I enclosed divided by L. This is the simplest method by which we can apply Ampere's law. Now, to demonstrate this idea, let us consider an example. We are coming to the example field due to a long straight conductor. It's a long straight conductor. Long means we say infinite, a conductor of infinite length, roughly say. It is a conductor of infinite length, very large length. And my requirement, so if let us consider that the loop carries a current I, and my requirement is to find out the magnetic field at a point P. Okay. What is our step 1? The step 1 is to identify a symmetrical loop which encloses this conductor. Okay, so I'm going to take a circular loop such that it is symmetrical. Why I am taking circle means circle will enclose this conductor. It is a loop. Sometimes you may tend to confuse by considering sphere. Sphere is not a loop, it is a closed surface. Circle is a loop, rectangle is a loop, square is a loop. They are all closed loops, I will say, closed loop. That means they do not possess a volume. The enclosed region has an area only, not volume. So loop, circle is a loop. We can construct a circle by means of a string. You can construct a square by means of a string. You can construct a rectangular by means of a string. So I have chosen a circle because circle will symmetrically enclose this conductor. Now if I consider a cross section of this conductor, if I consider the cross section of the conductor, you could see that it encloses a current I. This is that conductor, the cross section. It's a negligible cross section, I would say. The conductor has negligible cross section. The conductor has negligible cross section. Now, Ampere's last we told it is very simple. Magnetic field is equal to mu 0 I enclosed divided by L. Problem is over. It's that simple to apply Ampere's law, I tell you. It's as simple as that. Now tell me, what is I enclosed? I enclosed by this circle. The current is going upward. This is the Amperian loop. The Amperian loop encloses the current I. The loop. The current inside the loop. So if I say I have just taken the cross section of this conductor such that this current is coming out of the board. So this is mu 0 I divided by the length of the Amperian loop. This radius I have taken, this distance, perpendicular distance is R. What is the length of the Amperian loop? Length of the Amperian loop is, come on, what is the length of the Amperian loop? Length of the Amperian loop is 2 pi into small r. The length of the Amperian loop is 2 pi into small r. Ready? So that means the magnetic field due to a long straight conductor at a point P, which is at a perpendicular distance r from the conductor. The magnetic field due to a straight conductor carrying a current I at a point which is at a perpendicular distance r from the straight conductor is mu 0 I by 2 pi r, whose direction can be determined by the right hand rule. That is, here it is directed into the plane of the board, here it is coming out of the plane of the board. So this is the formula for the magnetic field between long straight current carrying conductor. Now we can see that the magnetic field is inversely proportional to R. Which means if I plot a graph between B and R, the shape of the graph is a rectangular hyperbola. Here also it is likewise. This is the shape of the graph between B and R, where R is the distance of the point from the conductor. I hope this is clear to you. This is the first example that we are going to discuss using Ampere's circular theorem. Now we will take the next example. The second example which I am discussing is field due to a long thin walled tube. Okay, before that let me discuss this. Okay, this is the second one I am discussing. Field due to a long conductor of uniform current density. It's a long thick conductor, I would say. It's a long thick conductor I am considering. This is nothing but the example 4.8 of the NCERT book. Example 4.8 of the NCERT book is what I am discussing here. This is a field due to a long thick conductor of uniform current density. Thick conductor. Okay. Now we will discuss this question as such. Let me consider this as a conductor whose radius of cross section is A. The radius of cross section of this conductor is A, and it carries a uniform current I. It carries a current I such that its current density is a constant. So I will write current density J is equal to I divided by pi A square. Current density J is equal to I by pi A square. What is I? It is the current enclosed by the cross section A. It's a current enclosed by the cross section A. Now my requirement is to find out the field at a point P. What is our step number 1? We have to apply Ampere's circular theorem. Yes, I am going to apply the Ampere circuit theorem. So the first thing I require is an Amperian loop. And I am saying that the point P is at a distance R from this conductor. Okay, you can take P anywhere. So the radial distance is R only. So what is our rule? We have a direct formula for doing this. The magnetic field at point P is equal to mu 0 divided by L. As we told, L is 2 pi R. Now the next question, mu 0 times current enclosed. What is the current enclosed by this Amperian loop 1? What is the current enclosed by that Amperian loop 1? You can see that the whole conductor, right? The whole conductor is inside this Amperian loop, which means the whole conductor is inside this Amperian loop. The whole conductor is inside this Amperian loop. Whole conductor is inside this Amperian loop, and the current enclosed is equal to current I, the total current. Hope it is very, very clear to you. Mu 0 I divided by 2 pi R. That is our equation number 1. Now I am going to take another point, say Q, which is at a distance x from this conductor. I want to find out the magnetic field at x. Again, I am going to apply Ampere's law. I want to find out magnetic field at x. So I am considering another Amperian loop of radius x. The question. Now this part I am giving a different color. Okay, so now tell me, what is magnetic field at Q? Okay, it's very easy to write the denominator, it is 2 pi x. One more thing we can easily write, that is mu 0. Now the question, mu 0 I enclosed by the length of the loop. Length is circumference of the circle. Length is circumference of the circle. Here the radius of the circle is x, so circumference is 2 pi x. Now the question, what is the current enclosed by the so constructed Amperian loop? What is current enclosed by the so constructed Amperian loop? It's very simple. It has to be the current enclosed by the rose colored part. Current enclosed by this rose colored part. Current enclosed by this rose colored part. What is that going to be? So let me take that current as I dash. Now I dash is equal to current density J into area. J into area, but here area is pi x square. Why pi x square? Because the radius of the circle is x. What is J? Already we have on board. I divided by pi a square, that multiplied by pi x square. Ready? So this is equal to I into x square divided by a square. That is I dash. I dash is equal to I into x square divided by a square. Right? Now the question is, what is BP? Sorry, what is BQ now? Which means BQ is equal to, substituting for I dash, mu 0 divided by 2 pi x, which can be written separately. Now I am going to substitute for I dash. What is I dash? I into x square divided by a square. Now we have an x square in the numerator, another x at the denominator, which will give you BQ is equal to mu 0 divided by 2 pi a square. That is a constant multiplied by x. So this is the magnetic field at a point inside. This is the magnetic field outside. The question is, if I say point O is the center of the circle, what is the magnetic field at O? Magnetic field at the center of this conductor. There you can take the x value is equal to, what is the value of x at the center? What is the value of x at the center? That is equal to 0, which means the magnetic field at the center is equal to 0. Now this is the answer you have to follow. The answer you have to follow is this much. Now what I will do is, I will write in general for this expression. So if with your permission I am doing it. So I can write the magnetic field B is equal to mu 0 I R divided by 2 pi A square for R less than or equal to A. And this is equal to mu 0 I divided by 2 pi R for R greater than A. This is the variation of magnetic field due to a thick conductor having uniform current density. Magnetic field due to a thick conductor having uniform current density. Now if I plot this as a graph, here we have seen the magnetic field is directly proportional to x. Here we have seen, the other case we have seen what? Here we have seen that magnetic field is inversely proportional to R, which means if I plot the same situation as a graph, see I am going to plot it as a graph. If I plot the same as a graph, the variation of the magnetic field will be with the distance R from the center. Magnetic field will be with the distance R from the center, At the center, this is, I am saying R is equal to small m. Okay, so I have mentioned R as the distance from the center, otherwise radial distance. The maximum value of magnetic field is at the surface of this conductor, which is mu 0 I divided by 2 pi A. Then you can get by substituting x is equal to A. If you put x is equal to A, mu 0, I am sorry, there is a mistake, mu 0 I into A by 2 pi A square, A and A will cancel. Now here what you see is, at the center it is 0. And for points inside the graph is a straight line because B is directly proportional to x. Here I have replaced x is R for us. Here B is directly proportional to R. So for every point inside the magnetic field is directly proportional to R. And for points outside B is inversely proportional to R. The shape of the graph here is a rectangular hyperbola. Here B is directly proportional to R. Here B is inversely proportional to R. Okay. B is directly proportional to R. This is B inversely proportional to R. Okay. This is the answer. Magnetic field with a thick conductor, long thick conductor having uniform current density. Yes, now we will go to another situation. So this is the field due to a long thin walled tube. This is the conductor I am saying. It's a thin walled tube. That means the current is supposed to flow in the region mentioned. And let me say this is carrying a current. The question, if I construct an Ampere loop here, I can easily understand this problem. I construct an Ampere loop. What is the magnetic field at the point P? It's very simple to say mu 0 divided by, if I say this radius is R, mu 0 divided by length is 2 pi R. What is the current enclosed? It's the current in the conductor as a whole, that is mu 0 I by 2 pi R. Now I'm going to take another point Q. The point Q is inside this thin walled conductor. Question is, what is the magnetic field at the point Q? I can easily say BQ is equal to, I am saying this distance is equal to x. Mu 0 divided by 2 pi x. Now question. What is the current enclosed by this Ampere loop? What is the current enclosed by this Ampere loop? Current enclosed by this Ampere loop. What is the current enclosed by this Ampere loop? 0. The answer is 0. So that means for all points inside the tube, the field is 0. For all points outside the loop, the field is inversely proportional to R. That means if I plot a graph between B and R, the graph is same as what we got in the previous equation, except for the fact that this is mu 0 I divided by 2 pi A and its maximum value. There is nothing here, everything is 0. Now field inside, here the magnetic field is equal to 0. Here the magnetic field is proportional to 1 by R. That's the answer. Here magnetic field is 0, here B is proportional to 1 by R. I hope this is clear to you. Now I would like to ask another question. A long straight conductor of uniform cross section has a uniform current density. The radius of cross section is A. Radius of cross section of the wire is A. Full stop. Find the ratio of magnetic field at P at a distance x less than A and Q at a distance R, which is greater than A. That means P is a point inside the conductor and Q is a point outside the conductor. So you will get me the answer for the ratio of the magnetic fields at P and Q, where P is a point at a distance x from the center of the conductor and R is a point, Q is a point at a distance R from the center of the conductor where R is greater than A. Now this is a very important question because we got similar questions, or what I am saying, this is a general formula you are going to get. General formula is what you are going to derive from here, and we had a question based on this concept for this year's GMAIN as well as 2017 NEET paper. So I request all of you to try this problem, and this should be and the correct answer to this problem has to be a formula such that this kind of problems can be done very easily. I hope you understand this video. Thank you.